Hi, this is Karthik. I'm a PhD student at Embry-Riddle Aeronautical University, and the other author is my professor, Dr. Mark Ricklick. Thank you for coming to this poster presentation. So, my area of research is vortex-induced jet oscillation used for heat transfer enhancement. So, on your left, you can see a gas turbine engine. So, typically, the efficiency of a gas turbine engine mainly depends on the turbine inlet temperature. So that is the temperature, that is the gases coming out of the combustion chamber. So if we increase the turbine inlet temperature, we increase the efficiency. So one way to increase the turbine inlet temperature is by gas turbine blade cooling. So going into internal gas turbine blade cooling, so on your bottom you can see a typical blade which is being cooled by multiple methodologies. So usually the jet impingement is employed at the leading edge of the blade because it has very high cooling effectiveness, and that is the hottest part of the blade. So that is where the total temperature comes into play, at the leading edge. So jet impingement is usually employed in a row, multiple jets. So on the bottom you can see the Nusselt number distribution over these row jet impingement. So you can see so many peaks, and also we can see if you can see the mean, it's going to go downstream. So this is due to the jet deflection due to the cross flow developed by the initial jets. And also these peaks that are formed in waves, so these peaks are due to the stagnation point. So each peak represents the point of impingement of each jet. So this Nusselt number distribution leads to thermal stresses and non-uniform temperatures. So coming into my research now, so on the top right you can see a jet impingement which is steady in nature, and a cylinder over which flow over which produces vortex sheddings. So we combine these two things to form our hypothesis, where we take the vortex coming out from the cylinder to interact with the jet to make it oscillate. So coming into the CFD, so preliminary investigation was carried out to define various effects of the geometrical and flow parameters on jet oscillation and also on heat transfer results. So on the right bottom of the CFD you can see the vortex coming out of the cylinder that interacts with the jet, and the jet usually oscillates. And on the bottom left of the figure you can see the jet oscillating from either end to other end laterally. And below that you have the plot. So we have three plot showing the effect of cylinder jet distance. So that is S by D of 2, 3 and 4. So 2 is non-oscillating jet and the other 2 is oscillating jet. So the red dotted line is the non-oscillating jet. You have a dip in the center, and this is due to the jet being curling around due to the cross flow effect. And whereas the oscillating jet is going to oscillate nicely and the dip goes away, and we have a plateau at the center. So further analysis is being carried out for other parameters to further increase the heat transfer distribution. And coming to the experiment, so under the experiment you can see the sketch of my setup, and below that is the photo of my setup. So initially we had to figure out where to keep this jet behind the cylinder. So we had to map out the turbulence intensity behind the cylinder using a hot wire. So we used these three different cylinder diameters, and we found out that cylinder diameters more than 1 is really good. So 2 and 3 we have good turbulence intensity, so we have high energy vortex sheddings which we can use for jet oscillations. And further heat transfer experiments are on the way using TSP, and that's all. Thank you. And any other further questions, you can contact me. It's in the bottom right. My email, you can contact me over there. Thank you.